Hey everyone, and welcome. I am absolutely thrilled to guide you through today's explainer. We are going to embark on a really fascinating journey deep into the microscopic mysteries of electricity. Think about it. You interact with electricity every single second of your waking life, from the device you're using right now to the lights above your head, all the way down to the very neurons firing in your brain. But have you ever stopped to actually think about how this invisible force flows through solid matter? Like, why do some materials let it rush through like a river, while others stop it dead in its tracks? Well, let's dive right in and unlock the quantum secrets that power our entire modern world. So I want to start by posing a really fundamental paradox of our everyday world, something so common we completely take it for granted. Why does metal shock you, but wood doesn't? If you were to accidentally touch a live wire with a metal fork, the results would be, well, disastrous. But if you touch that exact same wire with a dry wooden stick, you're perfectly safe. It's a simple observation, but the physics behind it are absolutely mind-blowing. Think about a standard charging cable. Inside, you've got a copper wire that conducts current completely freely, but surrounding it is a plastic casing that blocks that current entirely, keeping it safely contained. And here is the crazy part. Both the copper and the plastic are just made of atoms. They are built from the exact same fundamental building blocks of the universe: protons, neutrons, electrons. So why on earth do some materials absolutely love electricity while others completely reject it? To solve this mystery, we first need to agree on what electricity actually is. By definition, an electric current is simply the directed, ordered movement of an electrical charge. That's it. It's not magic. We just need charged particles, and we need them to move in a specific direction. If the charges can easily move, we have a current. If they're stuck in place, well, we don't. Now, if we zoom way, way down to the atomic level, we see a positively charged nucleus right at the center, and orbiting around it are our negatively charged electrons. The answer to our whole mystery is hiding right here, deep inside the atom. Specifically, it all comes down to how tightly those outer electrons are bound to their nucleus. Part 1. Conductors, the free movement. In metals, things like copper, aluminum, and silver, the outermost electrons are only very weakly attached to their parent atoms. They can easily break away and form what physicists actually call an electron gas. Imagine a massive open-field music festival where the crowd can easily roam around wherever they want. That is exactly what a metal is like. The electrons detach and form this sea of free, mobile charge carriers that just wander throughout the material. So when you apply an electric voltage, that entire sea of electrons immediately begins to flow together. The really crucial takeaway here is that only the electrons are moving, not the metal atoms themselves. And we actually have a super fascinating historical anecdote to back this up. Back in 1899, a German physicist named Carl Ricke set up a brilliant experiment at a tram substation in Stuttgart. He took 3 metal cylinders, 2 copper and 1 aluminum, pressed them tightly together, and ran the main electrical current for the city's tram lines right through them for over a year. When he carefully weighed and analyzed them afterward, he found 0 atoms of aluminum in the copper and 0 copper in the aluminum. He conclusively proved that the heavy atomic nuclei stay perfectly still. Only those tiny invisible electrons are doing the traveling. And the sheer scale of this electron movement is staggering. We're talking about 10 to the 23rd power. That's a 1 followed by 23 zeros. That is the approximate concentration of free-moving electrons in just a single cubic centimeter of a standard metal. It is a completely incomprehensible swarm of charge carriers, ready to instantly transfer power the second you flip a switch. And that is exactly why metals are such incredible conductors. Part 2. Insulators, the absolute blockading. Now, if a metal is a free-roaming crowd in an open field, an insulator, like dry wood, rubber, glass, or plastic, is like a stadium where everyone is strapped into assigned seats. In these materials, which we call dielectrics, the electrons are incredibly tightly bound to their parent atoms. They are completely locked in place. Even if you apply a strong electric field, those electrons simply cannot break free to carry the charge. Because there are no free charge carriers, the current is totally blocked. And that is exactly why the rubber on your shoes or the plastic on a wire literally saves your life. Okay, but now I want to introduce a little plot twist that kind of challenges our everyday assumptions. We all know that water and electricity are a deadly combination, right? We're taught from a young age never to use a toaster near the bathtub. So does water conduct electricity? The answer might actually shock you. Pure water, and I mean completely distilled H2O without a single impurity, is actually an excellent insulator. Its electrons are locked up tight in molecular bonds. It practically blocks current completely. But the water we interact with every single day, whether it's from the tap, in a river, or out in the ocean, is full of dissolved salts and minerals. And salt water is an excellent, highly dangerous conductor. So how does that work if the electrons in water are locked up? Well, when salts, like everyday sodium chloride, dissolve in water, they undergo a process called electrolytic dissociation. Basically, they break apart into positively and negatively charged ions. So in salt water, it's not a sea of free electrons carrying the current, it's the physical movement of these heavy charged ions drifting through the liquid. This is exactly why having wet hands makes you so vulnerable to electrical shocks. Your sweat contains salts, which instantly turns the moisture on your skin into a perfect ionic highway for electricity. Part 3. Semiconductors, the magic metal. Now for the really exciting stuff. To understand semiconductors, we need to talk about band theory. Think of energy states like levels on a ladder. To conduct electricity, an electron has to jump from a full valence band, where it's stuck, up into an empty conduction band, where it can actually move. The space between them is called the band gap. In metals, these bands overlap, so there's zero gap. In insulators, the gap is massive, essentially a brick wall. But semiconductors, like silicon, sit right in the magic middle. They have a small gap that can actually be crossed. Let's break down how this works step by step. At absolute zero temperature, a semiconductor is a perfect insulator. All the electrons are stuck. But if you add just a little bit of energy, maybe through heat, flash of light, or an electrical voltage, you give those electrons just enough of a kick to jump that narrow band gap, suddenly they cross over into the conduction band, and boom, current flows. The material literally decides to switch from an insulator to a conductor based on its environment. But scientists, being scientists, didn't stop at just waiting around for heat or light. They learned how to hack this entire system through a process called doping. By injecting tiny, precisely calculated amounts of impurities into a silicon crystal, we can actively engineer its conductivity. If we add phosphorus, we force extra free electrons into the material. If we add boron, we create a deficiency of electrons, leaving behind these positive empty spaces called holes. By combining these strategically, we gain absolute, microscopic control over exactly when and where electricity flows. Part 4. Macro impact. How electrons changed the world. Just think about the technologies we rely on every single day. Because we figured out how to control the jumping of electrons across a microscopic band gap in silicon, we were able to invent the transistor. And the transistor, it gave birth to everything. Without semiconductors, there is no internet, there are no smartphones in our pockets, there are no processors capable of running artificial intelligence, there are no solar panels converting sunlight into energy. The entire digital world, our modern civilization, is built entirely on our ability to control the flow of electrons at the atomic scale. It really makes you look at the device you're watching this on in a completely different light, doesn't it? It's not just a piece of plastic and glass. It's this beautifully orchestrated dance of billions of electrons, carefully guided by the quantum properties of atoms. You see, electricity isn't magic. It's physics at the atomic level. And this flow of power is the absolute foundation of our future. So if the digital world is just controlled electrons, what incredible innovations will they power next? Thank you so much for joining me today. If you want to keep understanding how the universe works, make sure to subscribe to the channel Code of the Universe, and I will see you in the next explainer.